All right, let's get right into it. Today, we're not just talking about medicine. We're going to look at antibiotics as these incredible strategic weapons in a microscopic war that's happening inside our bodies, which leads to a pretty fundamental question.
I mean, have you ever really thought about it? You feel awful, you take a pill, and somehow this tiny thing takes on billions of invading bacteria and wins. How does it do that? What is actually happening down on that battlefield?
Well, it's definitely not magic. It's pure strategy. And that's what we're going to break down today. The 3 core battle plans that antibiotics use to wipe out bacterial invaders.
But before we even get to the attack plans, we have to understand the #1 rule of engagement. You know, how do you attack the enemy without causing massive friendly fire to your own cells?
It all comes down to this absolutely brilliant concept called selective toxicity. Think of it this way. Our cells are the civilians, and the bacteria are the invaders. These drugs are designed like smart bombs that only target things unique to the enemy's armor, like their cell walls, something our cells don't even have. It's how we can wage this incredibly precise war right inside our own bodies.
So, let's jump into our first major strategy. If your enemy is holed up inside a fortress, well, the most direct approach is to just tear the walls down.
For a bacterium, that fortress wall is made of a really unique material called peptidoglycan. It's what gives it structure and protection. If you mess with that wall, the whole bacterium just bursts. It can't survive. So targeting the wall is a kill shot. But, and this is a key point, this attack only works if the bacteria are actively building. You can't really sabotage a construction site if no one's building, right?
And there are 2 really clever ways to do this. On the one hand, you've got beta-lactams, like penicillin. They work by essentially handcuffing the construction workers, these proteins that build the wall. If the builders can't work, the wall crumbles. Then you have glycopeptides, like vancomycin. They use a totally different tactic. They sneak in and basically hide all the bricks, covering them up so the builders can't use them. 2 different methods, same result, a collapsed fortress.
Now there is a much more, let's call it a brute force option. Some drugs, like polymyxins, act like a powerful detergent that just dissolves the bacteria's membrane. It's super effective, no doubt, but it's also a lot less precise and can end up damaging our own cells, so it can cause some serious collateral damage, especially to our kidneys. It's really a weapon of last resort. Okay, on to our second battle plan. If you can't get through the walls from the outside, why not just shut down the enemy's factories from the inside?
Every living thing runs on proteins. They're the tools, the machines, the whole shebang. Bacteria build their proteins in these little factories called ribosomes. And here's the kicker, another perfect example of selective toxicity. Their ribosomes are a different model from ours. They use a 70S model. We use an 80S. That tiny difference makes for a perfect target.
And there are a few different ways to sabotage the assembly line. Aminoglycosides are like gremlins that sneak in and make the machines build faulty, useless proteins. Tetracyclines, they just set up a blockade, so the raw materials can't even get into the factory. Macrolides basically throw a wrench right into the gears, jamming the whole production line. And then you have linezolid, which is kind of a specialized tool you bring out for the superbugs that have figured out how to fight off the other tactics.
All right, our third and final strategy. This one is maybe the most sophisticated of them all. It doesn't go after the walls or the factories. It goes right for the command center, the bacteria's DNA.
Just think of DNA as the master blueprints for the whole operation. If you can make those blueprints useless, you win. So quinolones come in and jam the DNA copying machine, which means the bacteria can't multiply. Rifampin is different. It blocks the reader, so the bacteria can't even read its own instructions to build anything. And folate inhibitors? This is really clever. They cut off the supply of a special ink the bacteria need for their blueprints, an ink they have to make themselves, while we just get it from our food. Perfect selective toxicity.
So we have all these incredible, intricate battle plans. But how does a doctor actually decide which weapon to use for a specific infection? This is where the real-world strategy comes into play.
It really boils down to this choice. Do you need a sniper rifle or a shotgun? If the doctor knows exactly what kind of bacteria they're fighting, they can use a narrow-spectrum antibiotic. That's the sniper rifle. It's precise, targeted, and super effective against one specific enemy. But if the situation is life-threatening and they don't know who the bad guy is yet, they might have to reach for a broad-spectrum antibiotic. That's the shotgun. It can take out a whole range of potential targets all at once.
Okay, so here's a quick question for you, tying some of these ideas together. The choice of weapon isn't just about the bacteria, it's also about the patient. So which one of these factory saboteurs has a nasty reputation for causing cosmetic damage in kids?
Yep, it's tetracyclines. They have this tendency to bind to developing bones and teeth, and they can cause permanent staining. This is a perfect example of a doctor having to weigh the power of a weapon against the potential harm it could do to the battlefield itself, which is, of course, the patient.
And this brings us right back to that golden rule we started with. This quote really says it all. The goal is always, always to harm the invader and not the person that they've invaded.
And you can really see this balancing act here. All the way on one end, you've got drugs like penicillin, which are incredibly safe because of that unique cell wall target. In the middle, you have things like aminoglycosides, very effective, but they come with known risks to your kidneys and hearing. And way over on the other end of the spectrum, you've got the polymyxins. They're the heavy artillery, the ones that can cause serious collateral damage and are only brought out when absolutely nothing else will work.
So if there's one thing to take away from all this, it's that there is no single magic bullet. What we have is an entire arsenal of highly specialized tools. Each one is a unique battle plan with its own targets, its own strengths, and its own risks. Choosing the right one is a huge part of modern medicine.
But here's the final, and honestly, the most urgent thought. This war isn't static. The enemy is smart. Bacteria are constantly adapting, evolving new defenses, and figuring out ways to counter our best strategies. So the really big question we're all facing now is, what happens when our battle plans just don't work anymore? What happens when our best weapons become useless? That is the terrifying challenge of antibiotic resistance.